Okay, welcome back everybody. Today we have a very exciting lesson. We are looking at instantaneous velocity. Now, last class we were looking at average velocity, right? So if you remember the equation for average velocity, it was in the x direction, it was equal to our displacement over our time interval. Okay, so if we expand this out, this would be calculated as x2 minus x1 over t2 minus t1. So this is the average amount, the average velocity something has as it moves between 2 points. Great, okay, that's pretty solid. But we want to look at instantaneous velocity today, and we're going to do this using two different methods. Okay, so there's two methods we'll look at. Now, the first method is going to be looking at an equation. We will learn how to write an equation to give us the instantaneous velocity. And the second will be graphically. We'll be looking at a graph, and we'll see how we can sort of draw on this graph and get an idea of the instantaneous velocity. So let's look at a scenario. Let me draw you my x-axis. Okay, here's my x-axis, the positive x direction. And the scenario is that we're going to go colonize another planet. So we all get onto a lovely, big, beautiful rocket ship, just like this one right here. It is very, very safe, very low risk of exploding and killing everybody on board. So we're all on board this rocket and we're floating out in space, and the time is 0 and its position, let's say, is 0. So we're at our initial position and nothing's moving. Okay, we haven't started the engine up yet, we're just standing still. Now what happens is the captain is ready to go, everybody's strapped in, he presses the button and the rockets ignite. So the rocket starts producing thrust and moving forward. And I'm able to give you an equation for the position of this rocket as a function of time. And the equation is 5 meters per second squared times time squared. This equation describes the rocket's x position as a function of time. Okay, now, what if I was to ask you a question? I could ask you, what is the rocket's average velocity in the first 10 seconds? Okay, let me ask this question. What's the average velocity of this rocket for the first 10 seconds? Well, the idea is that at some time equals 10 seconds in the future, the rocket will reach a point, some x position at this time. And then once we know what this x position is, we know the time interval, we'll be able to use our average velocity equation and calculate the average velocity. So what is the position going to be? Well, we can just use our equation for the position here. We know that x is going to be equal to 5 meters per second squared times 10 seconds squared, right? And this will be then 5 meters per second squared times 100 seconds squared. And you can see that the units here cancel out for the seconds squared, and we're left with 500 meters. So our x position here must be 500 meters. It has traveled 500 meters in 10 seconds. And so now we can easily calculate our average x velocity, and that will be delta x over delta t. And our displacement delta x, well, we went from 0 to 500, so that's going to be 500 meters, and our delta t is going to be, well, 10 seconds, right? So here we have an average velocity of 50 meters per second. That's going to answer the question for us. Good. Okay, not too difficult. But now, what if I ask you, instead, what is the instantaneous velocity of this rocket at 10 seconds? So at 10 seconds, at that one moment, how fast is the rocket moving? This is a different question. This is not, well, would it be 50 meters per second? This is a good way to start out. Do you think the instantaneous velocity at t equals 10 is 50 meters per second? I don't think it is. I would expect it to be faster than 50 meters per second. And the reason why is because the average velocity is exactly that. It's averaging up the velocity of the rocket at all positions from x equals 0 to x equals 500. And I think that it's going to be moving faster at t equals 10 than it was earlier. And so the average velocity is averaging in all of these low speeds. So it won't be an accurate measure of the instantaneous velocity. I mean, for example, just at the very beginning at t equals 0, we know that the rocket has a velocity of 0. It's not moving. So you're averaging in some very, very slow speeds with some higher speeds. And so that's not going to give us our instantaneous velocity at t equals 10. At least I don't think so. So what does it even mean to have an instantaneous velocity? Like, are we imagining if you freeze time and you take a snapshot and can you see how fast something is moving? I mean, that's sort of what we're asking, but it's not practical, right? If you freeze time, then there's basically no motion. So we can't really imagine freezing time to find the velocity at that one instant. We kind of always need to have two reference points so that we can find a displacement and a time interval. So we kind of always need 2 points to really get a measurement of how something is moving. You can't just freeze it, right? Okay, so what if instead of taking the average velocity over the first 10 seconds, we take the average velocity over a shorter time interval, some period of time that's closer to 10 seconds, and then maybe that average velocity will be closer to the instantaneous velocity that we're looking for. Let's try this out. Okay, I'm going to make a little bit of a table here. We're going to start out with a time, and then let me do this in yellows. Okay, so we've got time, we've got our position, and we've got a time interval, and we've got a displacement, and then we're going to have our average velocity. Okay, so let's look at this. Let's make a little table here for some different values. Something like this. Now, the time is measured in seconds, position in meters, time interval in second, displacement in meters, and our average velocity, remember the equation is delta x over delta t, and so this will be measured in meters per second. So those are the units. And we're going to be comparing everything with t equals 10, right? So at t equals 10, x is 500. Okay, this is our reference point that we're going to be trying to find the velocities for. And we already did 1 point, right? We said that when time is 0, x is 0. Our delta t then is going to be 10 seconds. Our displacement is 500 meters. And we saw that 500 over 10 is going to give us an average velocity of 50 meters per second. Okay, so this is going from t equals 0 to t equals 10. But like we said, that average velocity is probably too low because we're averaging in all of these really low speeds that happen at the beginning. So let's choose a tighter time interval. What if we're looking at the average velocity between t equals 9 seconds and t equals 10 seconds? Okay, so just a 1 second interval. In this last second, what is the average velocity going to be? Well, let's find our position x first. Okay, so x is going to be 5 meters per second squared times 9 seconds squared. So this is 5 times 81 meters. 5 times 81 is 405. Okay, so this is going to be 405 meters. Our delta t is just 1 second, right? 9 to 10, that's a delta t of 1. And our delta x here is going to be from 405 to 500, so that's 95 meters. And now if we calculate our average velocity, it's going to be delta x over delta t. So that's going to be 95 over 1, which is 95 meters per second. And right away you can see, yeah, it's a lot faster when we ignore the first 9 seconds and just focus on that last one. We have an average velocity now of 95 meters per second. Okay, This is a little bit closer to what we might expect the instantaneous velocity to be at t equals 10. What if we shrink this delta t even further? What if instead of 1 second delta t, we look at 9.9 seconds to 10 seconds? So our delta t is a tenth of a second. How does that look? Okay, well, what's our position going to be? It's going to be 5 times 9.9 squared. So this would be 9.9 times 9.9 times 5, 490.05. Okay. That's our x position here. And our displacement is going to be 9.95 meters. Okay. So over this last tenth of a second, the rocket moves 9.95 meters. And that means the average velocity is going to be 9.95 divided by 0.1, 99.5 meters per second. So it's even faster than what it was between 9 and 10 seconds. It's a little bit faster. Let's shrink this delta t even further to 1/100th of a second. Okay, if it's 1/100th of a second, it's going to be 9.99 squared. What's that going to be? 9.99 squared times 5, 499.0005. 499.0005 meters. Okay, and if we subtract this with 500, we see this is going to be 0.9995 meter displacement. Okay, and if we then calculate our average velocity, it's 99.95 meters per second. So it got even faster. Over this last 100th of a second, it travels at an average velocity of 99.95 meters per second. We could keep going. We could keep going, plugging in values with smaller and smaller delta t, trying to narrow in on exactly what that instantaneous velocity is going to be at t equals 10. But I think you see the same pattern that I do, and that this velocity appears to be approaching 100 meters per second. That's what it appears to be approaching. Now, I don't know conclusively if that's what it'll be. There's a chance it might wind up going to 100 point something. If we get a small enough delta t, that might happen. But right now, this is the pattern. So let's look at what we've been doing. Let's try and pull these lessons together. What we've been saying is that as delta t gets smaller and smaller, or let me write it as smaller delta t, what we see happening is we seem to be getting closer to the instantaneous velocity that we are looking for. Okay, smaller and smaller time interval winds up getting us closer and closer to this instantaneous velocity. So what we can do is we can define our instantaneous velocity and we will call this v sub x. So no average, just v sub x. This is going to represent the instantaneous velocity. And this is going to be the displacement over the time interval, same equation as we had for the average velocity, but we're going to say that as delta t, this time interval gets smaller and smaller and smaller. In fact, as it approaches 0, then it becomes the instantaneous velocity. So we're going to take the limit of delta t as delta t goes to 0 of delta x over delta t, and this value, whatever that value is in the limit that delta t goes to 0, will be our instantaneous velocity. So this should look familiar to you. If you've studied any calculus, you're going to know that this is essentially now the derivative of x with respect to t. And so we can now define the derivative here, and the derivative of x with respect to t is going to be equal to our instantaneous velocity. All right, let me try and unpack this a little bit. As we look at this expression here, we see that delta x is also going to 0, right? If you look over here, you can see that our displacement is shrinking. it's getting smaller and smaller. So delta x is going to 0. And delta x being in the numerator means that this entire expression is going to 0. Interesting. But also delta t is going to 0. And when delta t goes to 0, the denominator gets smaller. And so this entire expression goes to infinity. Right? So we sort of have these two trends that are acting against each other. Delta x going to 0 makes the fraction go to 0. Delta t going to 0 makes the fraction go to infinity. And so what actually happens is that the ratio of delta x over delta t does not go to 0, does not go to infinity. It goes to a finite value. And that finite value is the instantaneous velocity. Okay, so they kind of balance themselves out. And then here, this dx over dt is the derivative, right? This is the derivative of x with respect to t, okay? And if you know any differential calculus, you should be familiar with computing derivatives for different functions. So we have a function here for our position, and we can compute a derivative for it, so we can actually find an equation for the velocity. Let's do that right now. Okay. Our expression here is for x. First, I'm going to write it in more of a general form. Okay, so what we have is an expression where we have a constant multiplied by t to some power of n. And if we want to take the derivative of x with respect to t, we're going to use the power rule. And the power rule in physics is going to be your best friend. This is going to be the most common way that you will be taking derivatives. So if you want to learn just one one derivative equation, this is the one you want to learn. Okay, so this is going to become n times a times t to the power of n minus 1. So this is the power rule that you should have learned in math class. And like I said, it's the most common way that we will be taking derivatives in this course. Okay, so in our specific example, our x equation over here was 5 meters per second squared times t squared. Okay, so this is our position equation. And to take the derivative of this, it would now be, we take the n down, so it's 2 times 5, which is 10 meters per second squared, t to the power of 2 minus 1, which is just 1, which I don't have to write. So it's going to be 10 meters per second squared times t. This is our derivative of x, and that's going to be equal to our velocity. Okay, so the important idea is that our derivative of x with respect to t is going to be equal to our velocity equation. And in our case, it is 10 meters per second squared times t. That's the equation to find the velocity of this rocket ship. Now, you might see derivatives written down in a few different ways. There are sort of 3 different conventions that you can use to write down a derivative. So the first one we have is here, right? We can write it down as ΔxΔt, derivative of x with respect to t. But there are other ways of writing down a derivative. A popular way of doing this in physics is to write x with a little dot on top. X dot is the derivative of x. Okay, so that's another way you might see derivatives written. Another way is sometimes you can write a function down as x of t, for example. In this case, a derivative might be x prime of t. This is one kind of notation. So you might see an x prime of t notation. These are 3 different ways of writing down derivative of x with respect to t. Okay, so they're all the same, just different notations. So let's try it out now. Let's try and find the velocity of this rocket ship at 10 seconds. Well, this is going to be 10 meters per second squared times 10 seconds. So this unit here will cancel with this, and we will be left with 100 meters per second. And lo and behold, it matches what we anticipated it should be by brute force plugging in numbers. That's a good sign. So here we go. This is a very, very important thing that you have to remember. It's the fact that the instantaneous velocity is going to be equal to the derivative of x with respect to t. Okay, let's look at a few other little properties here for instantaneous velocity. Okay, the first thing I want to talk about here is the sign of your instantaneous velocity v sub x. So let's bring in our equation here that we just had. It allows us to see that v sub x is equal to the derivative of the position versus, with respect to time. So the idea here is that your instantaneous velocity has a sign. It could be positive or it could be negative. And the sign is going to depend on how you calculate it. So one thing we want to notice is that our time interval, delta t, the sign for delta t, will always be greater than 0. And that's because time is always moving forwards, right? So our final position is going to be a final time is going to be greater than our initial time, right? So delta t is always going to be greater than 0 unless you have a time machine, you can travel back in time. So what this means is that the sign for our velocity must always be the same as the sign for our displacement. And displacement could be positive or negative, right? And we can see this on an x-axis. So if this is the positive x direction, and we have, let's say, a particle over here, the particle could move from, let's say this is x1 to x2. In this case, the particle is moving towards the positive x direction. And so delta x equals x2 minus x1, and this is going to be greater than 0. It's going to be positive. Since delta x is positive, we know that our instantaneous velocity will also be positive. Likewise, if you had another particle here, and this was x1 and this was x2, then that means the particle would be moving towards the negative x direction. And so here delta x would be less than 0, would be negative, and so that means our instantaneous velocity must also be negative because it's moving to the left. It's moving towards the negative direction. So I think that's pretty straightforward, but I do feel the need to point that out. And the other thing I want to point out is that the sign of your displacement is not going to be equal to the sign of your actual positions of either x1 or x2. So let me illustrate what I mean by this. Let's say that this is the 0 position. Okay, so everything here is positive and everything here is negative. So let's say we have a position here. Let's say that this is x1 and this is x2. Okay, so our displacement is towards the right, towards the positive direction. So here we can see that delta x is going to be positive, right? But the actual positions for x1 and x2 are all going to be negative, right? So even though the position coordinate is negative, the displacement is still positive, and the displacement is what's important for creating your velocity. Velocity doesn't actually care about your specific position, it only cares about your displacement. Okay, so these are two little notes I want to have here about the sign for your velocity. Now the next thing I want to point out is how we have two terms in English. In English, we often use the words velocity and speed to mean the same thing. However, in physics, they are not the same. In physics, velocity and speed are two different concepts. Velocity in physics is a vector. Okay, it's a vector, and we calculate it by taking the displacement and dividing it by the time interval. Okay, so this is what we've been doing. No surprise here, and as we just saw, our displacement can be positive or negative. Okay, so there's going to be a direction associated with your displacement because displacement itself is also a vector. Now this is different from speed. Okay, speed is a scalar. And we're going to calculate it by taking distance over time. And the thing with distance is you can't have negative distance. Yeah, I guess you could have zero distance, so it could be zero. But other than that, it's only going to be positive. You can only traverse some positive amount of distance. And so speed will never have a sign associated with it because it is not a vector, it is a scalar. Now, there's some notation that we can talk about here. Okay, so we talked about our instantaneous velocity. Now, typically in this class, we're going to use a notation and we'll have something like v sub x. Or later on, if we have other axes, we're going to have v sub y or v sub z. These are going to represent velocities because the sub notation there shows that there's a direction associated. It's along a specific direction. And so it could be positive or negative, right? Instantaneous velocity is different from instantaneous speed. For instantaneous speed, we're simply going to use a v with no sub. And so here, it's going to be only positive or zero, right? So there's no sign associated with speed. There's no direction. Now you could add in a direction. So if you had a velocity, if you had a speed, you said v equals 10 meters per second east. So you add in a direction, now it becomes a velocity, right? Because you have added a direction into it. So a scalar plus direction equals vector, right? Good, okay. Now, the other thing I want to talk about is this difference between average velocity and average speed, because these are also not the same. Now, unfortunately, there's no simple notation, but if you write out average velocity or average speed, you'll see what we're talking about. As an example, let's say that we have a circle. Here's a circle, and we are going to be have this circle a radius of 10 meters. Let's say that you are right here. Here's your initial position, and you're going to walk around clockwise in a circle until you return to the same point. And let's say it takes you 12 seconds to walk around in this circle. Okay, so your average velocity is going to be your displacement over the time interval, but your displacement here is 0, okay? Your total displacement is 0 meters. And although it took you 12 seconds, that's going to give you an average velocity of 0 meters per second. So that's your average velocity because you actually didn't wind up changing your position. Average speed is going to be a little bit different, okay? This is distance over time. And distance, we see, is going to be equal to the circumference of the circles. This is going to be pi times the diameter, which is 2 times the radius over 12 seconds. And so we can plug in some numbers here, and we can see that pi times 2 times 10 times 20 is going to be 62.83 over 12 seconds. And this will give us about 5.2 meters per second for our average speed. And so we see that the average speed is definitely not the same as the average velocity because 5.2 is not 0. Okay, these are two different concepts that can be confused together. So I want to make sure that you get that straight. Okay, let's move on and look at a new graphic way of understanding what instantaneous velocity is all about. Okay, so now let's look at what the instantaneous velocity might look like graphically using this position versus time graph. And I've gone ahead and I've graphed out the function for our position of the rocket ship. And if you recall, the equation there was x equals 5 meters per second squared times time squared. So when we have a time squared here, this variable squared, we should expect that the curve looks something like a parabola. And that's exactly what this curve looks like right here. It looks like a parabolic arc, which is great. That's exactly what we are expecting. Okay, now our reference point or our target point that we were trying to find the instantaneous velocity for is right here. This is equal to t equals 10 and our x position is 500. Okay, so this is sort of our target point that we were computing the average velocity before. Now, before we were using equations, but now we're going to try and do it graphically. So similar to before, I'm going to make a little chart here for time, position, delta t, displacement, and then the slope of the line between these 2 points that we're going to be plotting out. Okay, so let me finish this over here. Great. Okay, so we're going to take 2 points on this curve and connect them with a line and then find the slope of that line. And that slope is the same as the average velocity of the rocket ship between those 2 points, right? So let's start out with t equals 0, and that's going to be right here. We can see t equals 0, x equals 0, okay? We can plot a line that's going to connect t equals 0 with t equals 10, and that's going to look something like this. Okay, so here is a line connecting to it. And if we compute the slope of this line, we will have computed the average velocity between these 2 points. So let's do that. Let's compute here delta t. Okay, so delta t looks like it's going to be from here all the way to here, right? So this distance here is our delta t, and that's going from 0 to 10 seconds, so it's a total delta t of 10 seconds. Our delta x is going to be similar. It's going from about here to here. So that's going to be 500 to 0, so delta x of 500. And the slope will be rise over run, so 500 over 10, that's going to give us 50 meters per second. That's the slope of this line. That's the average velocity between t equals 0 and t equals 10. Great. It's not very close to the instantaneous velocity at t equals 10, so let's try and find another point that's closer to t equals 10. Let's try t equals 5 seconds. Okay, let's try t equals 5 seconds. If we do that, t equals 5, I plot the point here on the graph, and eyeballing it, I'm seeing an x position of about 125. Okay, so now when we draw this line between these 2 points, the line looks like this. And as we can see, this second line is more steep than the first one. We should have a steeper slope, which is good. Let's see what this is actually going to be. So our delta t, it looks like it's going to be running from here to about here. So that's from 5 seconds to 10 seconds. That's a total length of 5 seconds here for delta t. And for delta x, we'll be going from here to 125. So 500 minus 125, that's going to be 375. So that's our delta x over there. And 375 over 5 is 75 meters per second. So that's the slope of this second line that we drew there. And it's steeper. It seems to be approaching the instantaneous velocity at t equals 10. Okay, let's find another point here that's even closer to t equals 10, and we're going to use t equals 9 seconds. So when t equals 9 seconds, let me plot this point right here. It's going to fall right here on the parabola, and I see that my x position is about 400. But if I was able to zoom in a lot, I would see it's not exactly 400, and we calculated this before. Let's take a look at what it was. So when we calculated it before, we saw that at t equals 9, x is actually 405. Okay, so it's a little hard to see on the graph, but it's actually 405. So we're going to run with 405 here for our x position. And now we're going to calculate the slope of a line between these 2 points. So let me plot that line. It looks something like this. And it's even more steep than the second line we plotted, right? So the delta t here is going to be from t equals 9 to t equals 10. So that's just 1 second total for delta t. And our delta x is going to be going from 500 down to 405. And so that's going to be a length of 95 meters. And so delta x over delta t is going to give us our slope of 95 meters per second. And as you can see, this is definitely approaching the instantaneous velocity of t equals 10 seconds. And we can try and imagine, as we take points that are closer and closer together, we reduce this delta t interval down to 0. What would this yellow line look like for that connects them together? Well, let's try and imagine. Let me bring in a blank one here. So we're looking at the point of t equals 10 seconds right here. And you can imagine that as these points get closer and closer together, the slope of that yellow line is going to approach a finite value. And what it's going to do is, it's basically, as these points get closer and closer together, you're essentially going to get a position where you have these 2 points are going to be basically just touching. The line is just going to graze the curve at this one point, and you'll get a line that looks like this. Okay, and what we call this yellow line is, we call it a tangent line, because it just kisses the curve at that one point. And that's what a tangent line does. And so when the distance between the 2 points goes to 0, delta t goes to 0, we get a tangent line over here. And the idea is that we can take the slope of this tangent line, and that will be the instantaneous velocity for the spaceship at t equals 10 seconds. So let's try and do that. Okay, let's look at what this slope is going to be. So I've got a point here. I can take 2 points here. All right, so let me get a delta t right here. So this is 13 minus 6. So that's going to give us 7 seconds here. And then from this distance here is going to give from 800 to 100. So that is 700 meters. So my slope is equal to 700 meters over 7 seconds, which is equal to 100 meters per second. And that is the instantaneous velocity at t equals 10 seconds. And this matches what we computed before using the equations. So let's compare. When we were looking at this before, we saw that the velocity equation was equal to delta x over delta t in the limit when delta t goes to 0, and that's equal to the derivative of x with respect to t. And what we're saying now is this is equal to the slope of the tangent line. So the slope of this yellow line is equal to the velocity, the instantaneous velocity, which is also equal to the derivative of the x function for this specific point. Great. Okay, let's compare this with some equations. So our equation for the x position is 5 meters per second squared times time squared. And so that means derivative of x with respect to time, which is our velocity, is equal to, well, the power rule, right? So that's going to be 10 meters per second squared times time. And that's the equations here. So let's compare this now for this point over here. So x of 10 seconds will be equal to 5 meters per second squared times 10 seconds squared. And this is equal to 100 times 5. That's going to be 500 meters. And that's what we find for our x position. Our x position here is 500 meters. When we compute now the velocity, our velocity is equal to 10 meters per second times 10 seconds. So this will equal 100 meters per second. And that is exactly the same as the slope of the line that we computed right here, the slope of the tangent line at that point. What this means is that when we look at the position equation over here, our position equation is going to give us, when we solve it, it's going to give us a point on the parabola, right? So the x position for that time is a point on the parabola. What the velocity equation does is, for every point on the parabola, it tells us the slope of the tangent line on that point on that parabola. That's really what the velocity equation is doing graphically. So what we can do is we can choose another point on this parabola and show that the tangent line at that point, the slope of that tangent is equal to the velocity using the derivative of the x position equation. So let's try plotting another point on this parabola. So let's choose another point on this curve. Let's try t equals 5 seconds. Okay, so t equals 5 seconds right here. And when I look at this, I see it has an x value of about 125. So this is position 5, 125 right here. Now let me try and draw a tangent line to this curve. And what I see is I'm probably going to get something that looks something like this. Yeah, I think that looks pretty good. So here I've drawn a tangent line that just kisses the curve right at this point of 5, 125. So t equals 5. We get this tangent line right there. Now, what can we do with this? We can try and find now the slope of this line, and that slope should be the instantaneous velocity of the spaceship when t equals 5. Okay, so let me find another point on this curve. Looks like here is a good reference point here. And here t is equal to 17. And my x position is about 725. Okay, so that's what I'm looking at over there. So my delta t is going to be from t equals 5 to t equals 17. So that's 12 seconds. And my delta x is going to be from 725 down to 125. So that's going to be 600 meters. And so what I can see here is my slope is going to be equal to 600 meters over 12 seconds. And that's going to be equal to about 50 meters per second. Okay, so that's going to be the slope of the tangent line at t equals 5 seconds. Let's try and compare this to the equation. So if we are the position equation here for x of 5 seconds, that's going to be 5 meters per second squared times 5 seconds squared. So 5 times 5 times 5 is going to be 125 meters. Good, that's what we had here for our x position that we saw on the graph. Now the velocity equation is going to be 10 meters per second times 5 seconds, right? So this is velocity of 5 seconds. And we can see that this is going to be 50 meters per second. Oh, I forgot a squared here. Okay, good. And so this is matching exactly what we observed graphically for the slope of the tangent line on that point on that curve. And this is really great news, okay? So we can see that graphically, the tangent line on the curve gives us the instantaneous velocity. And so as we look at the curve, we can imagine the steepness of the curve at that one point. That's the instantaneous velocity. And this instantaneous velocity equation here tells us something very interesting. It tells us that the steepness of this tangent line increases by 10 meters per second, right? So for every 1 second we move over, the steepness of this line increases by another 10 meters per second. So that's another way to interpret what this velocity equation is telling us. And we can see that's true because when x equals 0, the tangent line is going to be horizontal, right? When it's 1, it's going to be, the tangent line is going to be the slope of 10 meters per second. 2 is 20, 3 is 30, 4 is 40, 5 is 50 meters per second, which is what we got here. When t equals 10, it's going to be 100 meters per second, which is what we got here. So for every 1 second we gain, the steepness of the tangent line increases by 10 meters per second. Okay, this is really good. This is showing us how we can see the instantaneous velocity graphically. And there's just a few more things I want to go over about looking at these kinds of graphs. Okay, so what I want to do now is look at another position time graph and glean some insights about what's going on with a curve here. So here's a very simple xt diagram. And let's imagine that this diagram looks something like, maybe something like this. Okay, so sort of like a sine wave, but maybe not exactly. Great. Okay, now what we can do is we can define a few points on this curve and try and understand what's happening with the instantaneous velocity, with the velocity of the object at these points. So here I'm going to have a point, we'll call this A, and here we'll have B, here we'll have C, and then here we'll have D, here we'll have E, and let's have one more point over here. We'll call this F. Okay, great. So we've got 6 different points on this curve. And what we can do now is we can look at something called a motion diagram. Okay, so introducing a new idea here called a motion diagram. And a motion diagram is basically a snapshot of the system. Okay, at this one moment in time, how are things moving in the system? And we can imagine it's some kind of particle moving along the x direction with certain positions at different times. Okay, so to do this, we're just going to draw the x-axis. Okay, so let's draw a series of x-axes. Let's do that right like this. Okay, perfect. So I have created a series of snapshots here, and this is going to be when time is A, t equals B, time is C, time is D, time is E, and time for point F here. So what I'm going to do is I want to draw the particle on the axis. So when time is A, we see that the position of the particle is here at 0. Okay, so it is at position 0. What about its velocity? Can we draw a velocity vector here on this motion diagram? Well, we can. The way we'll do that is we'll try and draw the tangent line to the curve at point A. And if we do that, we'll probably end up with something like, yeah, something like this. Okay, so here might be the tangent line at point A. And what I want to do now is draw tangent lines at all of the other points as well. Okay, so at point B, it's going to be horizontal, just like that. And at point E, it's also going to be horizontal. At point C, we can imagine the tangent line is going to be maybe something like, yeah, something like this. Is going to be pretty close to the tangent line at point C. Meanwhile, at point D, the tangent line might look something like, maybe even less steep than that. Something like this. Okay, so that's the tangent line at point D. And finally at point F, looks like it might be something like this. Okay, so what I've done is I've gone ahead and I've drawn the tangent lines on each of these points. And remember, the slope of the tangent line is equal to the instantaneous velocity. So that's the important point, right? The slope of the tangent is equal to the instantaneous velocity. Okay, so when we want to draw the velocity here at on the motion diagram for time A, we see that the slope is going to be positive, and it's going to be pretty big. It's going to be a pretty big slope. So how we can do that is we can just draw the velocity on something like this. Okay, so we can say that this is going to be our velocity here. At t equals b, what's the velocity going to look like, and where's the position of the particle going to be? So let's draw the position first. The position is going to be pretty high in the positive x direction. So the particle we can draw is maybe going to be over here. This is where the particle is now. And the slope of this line, of the tangent line, is 0. So the velocity here is 0. So there is no velocity. So this is all we have. We only have the particle at this position with no velocity. Now we get to point C. At point C, the position of the particle it's still positive, right? It's somewhere here, but it's less positive than B. So it's probably going to be somewhere around here, about halfway between where it was at point B and 0. And in this case, what's the velocity? Well, we look at the slope of this line. The slope of this line is now going to be negative, and it's pretty steep. So that means the velocity is going to be very negative. So drawing a very negative velocity might look something like this. So now that's what our velocity is going to look like at point C. Let's look at point D. So at point D now, our position is now negative. Not very negative, but it is a little bit negative. So maybe our position of the particle is here, and the velocity is negative, but it's less steep than at point C. So the velocity magnitude won't be quite as big, but it will still be in the negative direction. So maybe the velocity here looks something like this. This might be the velocity at D. And then we go to E. Now at E, we can see the position of the particle is a little bit further negative than at point D, so it'll be like that. But the slope of this tangent line now is 0. So the velocity here is 0. And so there's nothing to draw for the velocity vector. And then finally we go to point F. And the position of the particle at point F, well, we're back here at 0, and the slope is now again positive. It's sloped positive, and it's pretty steep, maybe not quite as steep as at point A. So we can draw a velocity vector that looks something like this and maybe doesn't quite go as far as it was in point A. And this is how we can translate xt diagrams into motion diagrams. We can imagine here, the important point is that the steepness, the slope of that tangent line is going to be equal to the velocity. So we can have points where the tangent line is actually has 0 slope, like here and here, where you have a horizontal tangent line. You can also have tangent lines that are positive and negative, and the magnitude of that steepness, of the negative slope or the positive slope, is going to translate into how big the magnitude of your velocity vector is going to be. Okay, so it's a lot of stuff that we went over today. We went over instantaneous velocity, and we saw how to look at it both graphically and how to create an equation to calculate what the instantaneous velocity is. And the instantaneous velocity equation is going to be the derivative of the position versus time equation. We are going to go over some exercises about this in our next class. Check the link in the description below. There's going to be a PDF on that website that you can download. You can check out those exercises. We're going to go over them in the next lesson. If this helped you out, give me a thumbs up. Give me a sub. I really appreciate it. If you still have questions about this, and it's a big topic, leave those questions down in the comments below, and I will try to help you out with them. Thank you very much, and I hope to see you next time when we go over those exercises. Bye-bye.